Hello, my dear students, and welcome to Chapter 3. We're going to break this chapter into two parts, and there'll be at least two, but I'm thinking of assigning 3 or 4 exercises to it and taking you through sample problems and having little help sessions to actually focus in and spend more time on some of the topics in this chapter. Now, this chapter is titled Chemical Reactions and Reaction Stoichiometry, and this is where I lose a lot of people because in this chapter we will be covering and doing a lot of mathematical applications for chemistry. So, let's jump right in, and I don't know if I want to go to full screen with these. I have a little trouble sometimes backing up when my screen commands disappear. But stoichiometry, as defined here in your book, is the study of mass relationships in chemistry, but it's really just relationships. And as you'll often see, they are not simple 1-to-1 relationships. 2-to-1, 2-to-1 to 2, 1 to 2 to 4 to 6 to 2 to 1, etc. And a good example is our next slide, where we combine oxygen and hydrogen to form water. And you cannot, there is a law called the conservation of mass. And basically, it says this, with apologies to Antoine Lavoisier, that is how you pronounce his name, that matter can neither be created nor destroyed. Now, we do know that's not entirely true if we deal with aspects of nuclear chemistry. And thanks to Einstein, we know we can convert between matter and energy. But for our general chemistry study of reactions, matter can neither be created nor destroyed. When you go on to combine hydrogen and oxygen to make water, you will find that the mass of the reactants, the things you react, the hydrogen and the oxygen that you put together, equals the mass of the water that you produce. And so let's talk just briefly about these chemical equations and what they are and what they tell us. Like any good equation, we have two sides to the equation. And in chemistry, instead of an equal sign, we use an arrow, which can be read as equals, but more properly as react to form, or gives us, or yields. So 2H2 plus 1O2 react to give us 2H2O, or 2H2 plus 1O2 yields or produces 2 waters, or H2Os. And you see I'm going back and forth between the chemical name and the chemical formula. So when we talked about chemical names and chemical formulas last time, that is important information. So let's look at another reaction. Reaction where we burn a hydrocarbon, that is a substance made up of hydrogen and carbon. This particular one is called methane. It is CH4. It is a gas. We react it or burn it in the presence of oxygen. And so, in this chemical equation, we have some terms you need to know. Okay? We don't use an equal sign, we use an arrow, and then we have in our equation the chemicals that react and the chemicals that are produced. The chemicals that react are called reactants, typically, and for our purposes. I'm a biochemist, so I study a lot of enzyme catalyzed reactions, and we call them substrates, but reactant and substrate can be used interchangeably, and they react together to yield a product, and that is carbon dioxide, CO2, and water. See how I did that? Carbon dioxide, a gas, the gas you're producing when you burn glucose and your foodstuffs, and exhale, and the gas that plants take in to make sugar through photosynthesis, but also water. And you know, when you breathe out, you're producing metabolic water that, for example, if you blow onto a cold glass or a cold mirror, you can see that water vapor. But our purpose for this slide is to show that we have reactants on the left, and if I can go to the next slide, products on the right, connected by an arrow. We'll talk about those arrows when we talk about reactions later. And we're assuming that everything reacts on the left to give the products on the right, and that if you count, you'll see there's one carbon on this side and one carbon on this side. There are 4 oxygen atoms, 2 oxygen molecules. Oxygen is a diatomic gas, but this is just atmospheric oxygen. Almost 20%, 19 to 20% of our atmosphere is this oxygen gas. There's 4 of those atoms. If you look over here, there's 1, 2, 3, 4 oxygen atoms. And so we have equal numbers of atoms on each side. And if you could weigh the methane and the oxygen that reacted, the reactants, and if you could weigh the carbon dioxide and the water that was produced, the products, you would find that we follow and obey the law of conservation of mass. And that matter has neither been created nor destroyed. And thanks to Dalton, these atoms, the oxygen atoms, remain oxygen atoms. When we make new compounds or new substances, it's because we rearrange the atoms. We did not make a CO2 atom or a water atom. We made water molecules and CO2 molecules by rearranging the atoms in our reaction. One other thing you'll notice when this reaction is written, as we're going to be writing reactions, there are some features here. And that is, let's start with these small letters, lowercase letters in parentheses, and these should all be italicized lowercase letters, and they describe the state of the reactants and the products. G for gas, L for liquid. This water is hot and is being produced in air, and until it condenses, it is a gas, so it was designated a gas. Carbon dioxide, you know, is a gas. It needs to be under extremely high pressure and low temperature to be turned into a solid, and rarely a liquid. Solid CO2 is called dry ice. As we go through this, we have these states. There's 4 states. We're going to worry about solid, liquid, and gas, of course, the 3 states of matter. And if this were a regular class with students in it, I know somebody would throw their hands up and say, my high school chemistry teacher said there's a 4th state, and that is plasma. And yes, plasma is an electrically charged gas that does not have the actual properties of a gas when I teach this. I usually have a plasma ball going in my classroom. But this is what happens when someone who's not a real chemist teaches chemistry, because there are probably 8 or 9 or more states of matter where you don't have the true properties of solid, liquid, or gas that we have to redefine. Sol gels or Newtonian solids or different things that you can define. I'm trying to think of some of the other ones that we have out there that do not fall into that. But for our purposes and in our world, 99% and greater of all the compounds and substances we encounter are going to be solid, liquid, or gas. Although frequently we can take a solid, such as table salt, and dissolve it into water and form an aqueous solution. And this is important because we have a chapter coming up where we study reactions in aqueous solutions. And it's important to me as a biochemist because we are big bags of water walking around where all the chemical reactions, metabolism of life occur, for the most part, in water. So, aqueous chemistry is going to become very important to us. Plus, in the laboratory, you've seen chemists, they're always moving test tubes around and they dissolve stuff in water and then react it. That's a very common chemical tool, besides the fact that it's important to life and biochemistry. Now, the other thing you'll notice in this equation up here, where we've written the reaction of 1 methane with 2 oxygen gives 1 carbon dioxide and 2 water, that I could do the count because I saw I have 2 oxygen molecules, 4 oxygen atoms in my reactants, but that was 2 oxygen. And so I have a coefficient in front of the oxygen and the water. Whole number, large coefficients, not large, but regular numbers as opposed to a smaller subscript, and we'll be dealing with some superscripts when we talk about ions or maybe isotopes. But these coefficients are written in front of each compound and tell us how many of them we are going to react. The 1 is understood, so we don't need to write 1 for our coefficient if we have 1 of something reacting or 1 of something produced. So this is important, and this is where I lose people, because don't forget, we must obey the law of conservation of mass. The number of atoms on the left must be precisely the same as the number of atoms on the right. Reactants and products have to have the same atoms on both sides. They're rearranged, but they have to total the same. And of course, that means the mass is conserved. So we have the law of conservation of mass because Antoine Lavoisier and his contemporaries didn't know very well about atoms. Certainly not their structure, though Dalton taught us that this is the way it's going to work. So, if you change the subscript, as we practiced in the last chapter, you will change the formula, the substance. So, you can change the coefficient to change the amount, but you cannot change the subscript. That's a big no-no, because if you do that in your reaction, you will be changing the substance. So if you want to, for example, change I guess their example here is water versus hydrogen peroxide. Instead of H2O, and of course the 1 here is understood, we make H2O2. Well, we'll make a totally separate substance. And there's a joke about two chemists walk into a bar, or how about a restaurant, and they say, what do you have? And the first chemist says, I'll have a glass of H2O. And the next person, who's not a good chemist or doesn't know how to communicate scientifically, says, I'll have a glass of H2O2. In other words, TOO, not TWO, but they give him a glass of hydrogen peroxide and he drops dead, which he might well do if you use some of the hydrogen peroxide, for example, that I have in the lab. The stuff you buy in the store in the brown bottles at Walmart is just a few percent, and I can get 70% hydrogen peroxide. We deliver to the school, of course, which is extremely dangerous and very challenging to work with. But my point is these coefficients, when you are balancing equations, and we're going to practice this, and I'm going to give you an exercise on it, we are balancing coefficients because we're going to be moving into a mathematical, quantitative discussion in chemistry. Remember, we always are measuring things in chemistry, and we're always quantifying them because we want to know how much of a toxic chemical is present, or how much of a valuable chemical we have, or how much of another expensive chemical we have to buy. So when we work with these reactions and these chemical equations, the substances will be pretty much defined, and therefore their formulas. It's the coefficients we're going to change when we balance our reactions, and for all those subsequent operations I'm alluding to that we will get to in the next lecture, you have to start with a balanced equation. And that is what we'll do. So, let's talk about some reactions. I have no idea why they started out this way, but we'll go with it. There are many, many types of reactions, okay? Combination reactions, where you have, for example, A plus B goes to C. And, well, here's a small list of them, but I'm going to list some other. Let me talk about them. So, a good example is when I burn magnesium in the lab, a magnesium ribbon, and I form that beautiful white powder. It's actually a good pigment for paints and the like, and form magnesium oxide. And these are pictures of it occurring here with the white powder of magnesium oxide being formed. And you see A plus B went to C. Magnesium plus oxygen formed magnesium oxide. And it was 2 magnesium with 1 O2, 2 atoms of oxygen, but only 1 molecule of oxygen to form 2 magnesium oxide solids. And of course, the oxygen was a gas present in our atmosphere, and the magnesium ribbon is just a sample of some magnesium metal. And this is a classical combination reaction. A plus B goes to a new compound C. Some people write it A plus B goes to AB. And that's true if you're talking about individual atoms. Okay, but here in this other example where you brominate a sample of propane, it's not so simple as A plus B goes to AB. You make a whole new compound C, okay? I don't want to confuse things, and it's best just to describe the reaction. A decomposition reaction, and by the way, these combination reactions are also called, depending on what book you read and where you're from, you may have heard it differently in a previous chemistry class. They're called addition reactions or perhaps a synthesis reaction, although you can have a synthesis reaction where you have more than two or more substances reacting, and you may form one or more products in a synthesis reaction. Combination reaction, more than two things can combine, sometimes three things combine. In a decomposition reaction, you may have heard this called a degradation reaction. Excuse my writing, reaction. My Apple Pencil is not the neatest thing, although I can program it to change my writing to typewriter form, and I probably should. Or also a breakdown reaction, where something decomposes or breaks down. You start with A and you break it down into B plus C. You'll also see some different books call this AB, breaks down into A plus B, where they're separated from one another or no longer combined. So don't get too hung up on the terminology, and one thing I won't be testing you over is the specific, nitpicky aspects of the terminology. But if you are given a reaction like this, and I say what type of reaction it is it, of course on a test you'll have choices, and I will use your book's terminology, but you would correctly choose decomposition reaction over addition or other reactions. And then this last one for now is called a combustion reaction. But before I just briefly describe it, there are many other types of reactions. I can think of many. And the other ones you may have heard of are substitution reactions. I don't have room to finish that word. Substitution reactions, single substitution, double substitution. Sometimes they're called replacement reactions, single and double replacement. In biochemistry, we like the terminology double displacement reaction. There are oxidation reduction reactions. In fact, combustion reactions are a type of redox or reduction oxidation reactions. And of course, there are nuclear reactions, and the rules and the guidelines we follow are going to shift, and we'll need new rules for those reactions. But we're not going to cover much in the way of nuclear reactions. I just want to say that there are many types of reactions. In combustion, of course, there are some properties of a combustion reaction. We tend to be breaking down organic carbon-containing compounds, and we tend to burn them in oxygen, and we produce two common products, carbon dioxide and water. And this is really for historical purposes, which I'll talk about later. Let's see, combustion reactions. Yes, so briefly, let me talk about that law of conservation of mass. So we learned about atomic weight, atomic mass, technically average atomic mass, unless you're talking about a purified single isotope. And if you put things together like calcium chloride, CaCl2, common drying agent because it tends to soak up water and things too. Calcium chloride, sodium chloride, any of those, we have to know about their formula weight, the sum of the atomic masses for all the atoms in the chemical formula. And for calcium chloride, calcium is group 2, it's always 2 plus. Chloride is group 7, it's always minus. So I need 2 of these, 2 chlorides, to balance the single calcium, plus 2 calcium. And calcium, if you look in the periodic table, you'll see that it has an atomic mass of, average atomic mass of 40.08. Chlorine has an average atomic mass of 35.453. I might have mentioned there are two main isotopes of it in approximately equal amounts, and so we get this kind of fractional atomic mass unit here. And there's two of them. So you add that up, and 35 and a half and 35 and a half is about 70.1. And calcium's about 71. 35 and 35 is 70, and a half is almost 1, and 40. You add that up, and you get about 111. 110.99 atomic mass units if you're talking about a single formula unit of calcium chloride. Now that's for an ionic compound, because as you remember, it's very unlikely you'll find a single calcium chloride. In its crystalline structure, these are coordinated to many different atoms, just like the sodium chloride was in that cubic structure we saw. And this is the chemical formula for this ionic compound, calcium chloride, and this is we call it its formula weight or formula mass. Molecular weight or molecular mass, either one. I prefer molecular weight because that's what I've learned. A lot of books are very strict about calling it molecular mass. Is the sum of all the atoms. So if you take this gas ethane, and it has 2 carbons, and attached to each carbon are 3 hydrogens, it's a gas. In fact, this is the gas that comes in through your pipes if you live in the city, and that you burn on your stove and your water heater and your house heater if you burn city gas. If you live in the country, you get propane, which is actually has an extra carbon and more hydrogens. Now, carbon has a mass of 12.011, but I'm just going to call it 12. And hydrogen has a mass of 1, but there are 6 hydrogens and 2 carbons. So 2 carbons is 24, and 6 hydrogens is 6, and it adds up to a molecular mass of 30 for this. But I told you before, I'm not really, I don't use atomic mass units a lot because we never work with a single atom or a single molecule, or in the case of ionic compounds, as I said, there's no simple group of atoms to call a molecule. They tend together. So we use its simplest whole number ratio of atoms, like 1 sodium to 1 chloride, sodium chloride, or 1 calcium to 2 chlorides and calcium chloride, etc. But before I do composition, okay, well, I'll come back to this. Let's do percent composition. So, one of the things we like to do is determine the composition of a compound. And it used to be much more important. It seems we know the composition of everything, but we want to teach you how to do the quick calculation of something. And this has real value. For example, I have a big jar of silver nitrate. Okay, and people want to know how much silver is really in there. And there's a simple way to do it, and that is to take the mass of all the atoms together, 3 oxygens, 1 nitrogen, and 1 silver, and add it up, and take the mass of silver and divide it by the total. And that's exactly what you do. So, in this example that we're going to look at, to do the percent composition, if we go back to that compound ethane, which is 2 carbons and 6 hydrogens. I should have drawn it where I have more room to draw it, but I'll just put my hydrogens up in the writing there. And remember, it is C2H6, 2 carbons and 6. What percent of that is carbon? That's a legitimate question. And so we just calculated that the ethane has a formula weight or formula mass or molecular mass of 30. And 2 carbons, each carbon's 12, 12.011. And so they have a combined mass of 24. And 24 divided by 30 is almost 80%. Okay? So 79.887, but for our purposes, 80%. So ethane is 80% carbon, and you can do the same calculation with the percent hydrogen. You can say it's 6 times 1.0, whatever the mass of hydrogen is in the periodic table, divided by 30, and you would get 6 over 30 and get 20%, or in the case we have here where we only have 2 elements, if the carbon's 80%, the hydrogen must be the remaining 20% of the mass, and it is. So that's percent composition. That's going to become important. Now, I want to talk just about 2 more things, and then we're going to stop before we move on to some of the quantitative aspects and practice balancing equations. But I want to say that when I tell you that I have, 24.022 atomic mass units of carbon, that is an incredible, non-functional, non-useful value. And I say that because I thought I had it somewhere here, but 1 atomic mass unit, let me pick a new color so it's different, 1 AMU, okay, is equal to 1.6605 times 10 to the minus 24th grams. That's minus 24. Let's see if I can take that out of there and make it a little neater. Minus 24 grams. That's a fleetingly tiny mass, and I can't even comprehend it. And so this is not very useful to a chemist working with AMUs. But those atomic masses that you see on those periodic tables are extremely handy. Every chemistry classroom, every chemistry lab, every industry lab, every research lab, everywhere I've been, there's always a big periodic table hanging up, and there's a good reason why, and you'll see, because we're going to use it quite a bit. Now, there is a man, an Italian, who was working with gases, and he saw that different volumes of gases, as long as they're at the same temperature and pressure, if you had equal volumes of gases, they had equal numbers of molecules. And it didn't matter whether the gas was carbon dioxide or water gas or oxygen or nitrogen or carbon monoxide. If you had equal volumes, they had equal particles, even though they may have totally different masses. Oxygen weighs 32, 2 times 16, 2 times 15.99997, or whatever it is in the periodic table. But for our purposes, it has a mass of 32, oxygen. Hydrogen has a mass of 2, 2 times 1, or 1.0017, whatever it is, up there in that periodic table. I'm sorry, I don't have one in front of me right now, but it has a mass of 2. And yet if I've got a container of hydrogen and a container of oxygen in the same room at the same pressure, the oxygen might weigh 32 grams, and it may weigh 16 times as much as the hydrogen, but there'll be equal number of particles there. And we have this substance, this SI constant, System International, International System of Nomenclature constant, called Avogadro's number, and it is abbreviated N with a small capital A. Do not let anybody tell you it's a small a, because it's named after Lorenzo Romano Amadeo Carlo Avogadro, Conte di Quaregna y Cerreto. That means he was the Count of Quaregna and Cerreto. In fact, he was born to a noble family related to the King of Sardinia in Italy, though he lived in Turin. And he lived from, you don't need to know this, 1776 to 1856. I have to know this because I used to have to say light a match and say his whole name, Lorenzo Romano Amadeo Carlo Avogadro, Conte di Quaregna and Cerreto, before the match burned me, to join the Chemistry Honor Society. That's called hazing, and that's against the law now. But it wasn't so much in 1974. Anyway, Mr. Avogadro did some amazing work. He was actually a high school teacher of physics and math, but he studied these gases and showed that the molecular weight, the molecular mass of a gas could be calculated from the mass of a sample of that gas if you knew the volume at a given pressure and temperature. And so Avogadro's number is the number of molecules that helps us use measurable amounts of substances. And so those molecular masses, one atom of carbon-12 is how we define our atomic mass unit, and one atom of carbon-12 has a mass of 12 atomic mass units. But what's cool is that if you have this quantity, one Avogadro's number, 6.021476 times 10 to the 23rd atoms, then this element in the periodic table, if you have that many atoms of that element, that's its mass in grams. Okay? So carbon, 6.02 times 10 to the 23rd atoms of carbon, if you look at the mass number, forget atomic mass units, that's how many grams that many atoms weighs. Now, it's inelegant for me to say 6.02 times 10 to the 23rd atoms of oxygen, or molecules of oxygen, since it's diatomic. So it would actually weigh, if I had 6.02 times 10 to the 23rd molecules of oxygen, it would weigh 32 grams. So we call that a mole. And the mole is abbreviated. We can't use M because that's meters, and we can't use MO because I guess that's molybdenum or something. So we don't get much of an abbreviation for the mole. It's MOL. But that mole is Avogadro's number. The mass of 1 mole of substance is the molar mass. So 1 mole of oxygen, as I said, has a mass of 32. Water, oxygen 16, hydrogen's 1, H2O, 2 hydrogens is 2, oxygen 16, has a mass of 18 grams per mole. And that's about a swallow. That's about, oops, I didn't mean to do that. I'm trying to enlarge this, but it's not letting me do it. That's about that much, a big swallow of water. And a mole of sodium chloride is about 58.45 grams. That's a lot of salt. But this is a laboratory amount, an amount that I can go to a balance and measure and weigh out. This is a very valuable tool, and we're going to be using moles extensively as we move into the last part of Chapter 3. And we can convert between them, because if I say I have 18 grams of water, and I know the molar mass, that 1 mole equals 18 grams, then I know how many moles I have. And when we were looking at those reactions where I have 2 hydrogens plus 1 oxygen gives me 2 H2O, I'm not thinking about individual atoms anymore. I'm going to read this 2 moles of hydrogen, that's a measurable amount, plus 1, the 1 is understood, but I'll write it down, 1 mole of oxygen gives me 2 moles of hydrogen. This, by the way, weighs what? Oxygen 16, O2 is 32 grams per mole, and if I have 1 mole, I have 32 grams. Hydrogen weighs what? It's element number 1, has a mass of 1.00, I want to say 117 or something, but that, and by the way, we are on our last slide here. I'm saying that for several of the people here. This hydrogen has a mass of 2 grams per mole, but I have 2 of them because I have a coefficient of 2. Don't forget those coefficients. So I have a total of 4 grams. Here I have 32 grams. And we just, in the last slide, said what? Water is 18 grams per mole. So these 2 waters have a mass of 18 grams each, or 36 grams. And I think you see now how we're going to be using this. So 2 moles of hydrogen plus 1 mole of oxygen gives 2 moles of water. Look at the exercise and practice balancing some equations. And I think I'll wait a day, but I will make sure we have a couple of weeks up, and I'm going to get a couple weeks ahead. And I will post the following lecture for the second half of Chapter 3 tomorrow. So, go through this, practice with exercise 3.1, and then we'll do the next part of this chapter. I recommend waiting a day or practice balancing equations. But as you do them, those aren't atoms anymore. Those are moles of substance, that quantity using Avogadro's number. And by the way, we can also calculate number of representative particles, and at a later date, we'll even be measuring or being able to use that to calculate volumes, if it's gases, and number of actual particles, and it's going to be extremely handy. So, once again, Avogadro's number, 6.02 times 10 to the 23rd. I had to memorize it out to 10 places for my induction into the Chemistry Honor Society, but 6.02214076 times 10 to the 23rd, sir, is Avogadro's number, and Until the next time, stay safe, and I will be posting that exercise at the same time as this. Give that a shot, and I will say goodbye for now. If I can find my record stop button. Goodbye now.